B. The roles of Europe and China in the evolution of ecumenical science. Note: Presidential address delivered to Section 10, General, on 31st August 1967 at the Leeds meeting of the British Association. The present paper was given in preliminary form as an address at the opening of the permanent exhibition of Chinese medicine at the Wellcome Historical Medical Museum in London on 28 March 1966. End of note. Many historians of ideas and culture still blandly assume that the Asian civilizations had nothing that we should call science. If slightly better informed, they are apt to say that China had humanistic but not natural sciences, or technology but not theoretical science, or even correctly that China did not generate modern science, as opposed to the ancient and medieval sciences. This is not the place to set such ideas to rights in any detail, but my own experience has shown that it is comparatively easy to produce a whole series of bulky volumes about the scientific and technological achievements which the Chinese are supposed not to have had. If, as is demonstrably the case, they were recording sunspot cycles a millennium and a half before Europeans noted the existence of such blemishes upon the solar orb. Note: Science and Civilization in China, Volume 3, pages 434 and following. If every component of the parhelic system received a technical name 1,000 years before Europeans began to study them. Note: Science and Civilization in China, Volume 3, pages 474 and following, and Ho Pingyu and Needham, 1959a. And if that key instrument of scientific revolution, the mechanical clock, began its career in early 8th century AD China, rather than, as usually supposed, in 14th century AD Europe. Note: Science and Civilization in China, Volume 4, Part 2, pages 435 and following, and Needham, Wang and Price, 1960. End of note. There must be something wrong with conventional ideas about the uniquely scientific genius of Western civilization. Nevertheless, it remains true that modern science, i.e. the testing by systematic experiment of mathematical hypotheses about natural phenomena, originated only in the West, yet it cannot even be maintained that China contributed nothing to this great breakthrough of modern science when it occurred in the later stages of the European Renaissance, for while Euclidean geometry and Ptolemaic planetary astronomy were undeniably Greek in origin, there was a third very vital component, the knowledge of magnetic phenomena, and the foundations of this had all been laid in China. Note: Science and Civilization in China, Volume 4, Part 1, pages 239 and following, 334, and Needham, 1964, page 255. There, people had been worrying about the nature of magnetic declination and induction before Westerners even knew of the existence of magnetic polarity. But from the time of Galileo, 1600, onwards, the new or experimental philosophy of the West ineluctably overtook the levels reached by the natural philosophy of China, leading in due course to the exponential rise of modern science in the 19th and 20th centuries. What metaphor, then, can we use to describe the way in which the medieval sciences of both West and East were subsumed in modern science? The sort of image which occurs most naturally to those who work in this field is that of the rivers and the sea. There is an old Chinese expression about the rivers going to pay court to the sea. Note: Compare Science and Civilization in China, Volume 3, page 484. End of note. And indeed, one can well consider the older streams of science in the different civilizations like rivers flowing into the ocean of modern science. Modern science is indeed composed of contributions from all the peoples of the Old World, and each contribution has flowed continuously into it, whether from Greek and Roman antiquity, or from the Islamic world, or from the cultures of China and of India. Here I shall confine myself to the Chinese case. In considering the situation before us, there are two quite distinct questions to ask. First, when in history did a particular science in its Western form fuse with its Chinese form, so that all ethnic characteristics melted into the universality of modern science? And second, at what point in history did the Western form decisively overtake the Chinese form? We may thus try to define the date at what may be called the fusion point on the one hand, and that of the transcurrent point on the other. Since by a historical coincidence the rise of modern science in Europe was closely accompanied by the activities of the Jesuit mission in China, Matteo Ricci died in Peking in 1610, there was relatively little delay in the juxtaposition of the two great traditions. Since the breakthrough occurred in the West, the transcurrent point for each of the sciences naturally preceded the fusion points. But as we shall see, the interest lies largely in the lag or delay between the two. First, let us consider the fusion points, those estuaries in time when the rivers flowed into the sea, and when full mixture took place. Here at once we find a remarkable difference between what happened in the physical sciences and in the biological sciences. On the physical side, the mathematics, astronomy, and physics of West and East united very quickly after they first came together. By 1644, the end of the Ming dynasty, there was no longer any perceptible difference between the mathematics, astronomy, and physics of China and Europe. They had completely fused. They had coalesced. If at first it seemed that Western mathematics had been at a higher level than Chinese mathematics, this was found to be due, as the decades went by, to a loss of the expertise which the Song and Yuan algebraists had had, and the restoration of their techniques redressed the balance. Though the lack of deductive geometry remained a debit on the Chinese side, Chinese mathematics had always been, by preference, algebraic rather than geometrical. Note: a full account of the history of Chinese mathematics is given in Science and Civilization in China, Volume 3, pages 1 to 168. End of note. Astronomy differed between the civilizations in an equally fundamental way, for while Greek astronomy had always been ecliptic, planetary, angular, true and annual, Chinese astronomy had always been polar, equatorial, horary, mean and diurnal. This epigrammatic formulation was due to Leopold de Saussure, see Science and Civilization in China, Volume 3, page 229. The two systems were not in any way opposed or incompatible. It was just as in the mathematics, the attention of Chinese and Europeans had been concentrated upon different aspects of nature. If the Chinese had never had the passion for geometrical models, which produced the Ptolemaic epicycles and ultimately the Copernican solar system, their medieval cosmology had been far more modern than that of Europe, for instead of crystalline celestial spheres, they thought in terms of infinite empty space and an almost infinitude of time. Note: compare Science and Civilization in China, Volume 3, pages 408 and 438 and following. End of note. By 1673, when Ferdinand Verbiest was reconstructing the Peking Observatory and equipping it with the new instruments even more accurate than the splendid 13th century ones of Kuo Xiu Qing, note: Science and Civilization in China, Volume 3, pages 350 following, 367 following, 451 following, end of note. This was perfectly understood, and the seal was set upon the matter when early in the 18th century Antoine Gobi published his great works on the history and theory of Chinese astronomy. Note: for the works of Gobi, see Science and Civilization in China, Volume 3, pages 760 and following. Since the breakthrough occurred in Europe first, Europe contributed rather more, giving up its crystalline celestial spheres, but introducing more refined calendrical computations, giving up its Greek ecliptic coordinates, note: Science and Civilization in China, Volume 3, pages 266 and following, but opening the way into those undreamt of worlds which the telescope would shortly reveal. Note: compare Pascal, Dahlia, Needham and Liu Guizhen, 1966a. And above all, introducing the new celestial mechanics and dynamics of the age of Galileo. Unified astronomy, of course, profited greatly by the records of celestial phenomena. eclipses, novae and supernovae, comets, etc., which Chinese astronomers had kept as accurately as they could since the 5th century BC, and in greater abundance than any other culture. Note: Science and Civilization in China, Volume 3, pages 409 and following. These records are in constant use by astronomers at the present day. Compare, for example, the current discussion on a nova of 1006 AD by Goldstone, 1965, Goldstein and Ho Ping Yu, 1965, Minkowski, 1965, Marsden, 1965, Gardner and Milne, 1965, and another on the secular deceleration of the Earth involving ancient eclipse records by Kurat, 1966. End of note. Lastly, one must take account of the fact that if ecumenical astronomy today uses exclusively the Greek constellation patterns, this is not in the slightest degree due to any inherent superiority of these over the entirely different Chinese ones. It is simply a side effect which followed upon the meteoric rise of modern science in the West as a whole. Men like Flamsteed or Herschel would have thought it bizarre to speak of Hui Xiu or Tianqi instead of Scorpio. Note: Schlegel, 1875, pages 153 and following. End of note. But there is no intrinsic reason for this. It was an incidental result of the rise of modern science in Western civilization first. One must always be on the lookout for such side effects. At all events, by the mid-17th century, the union of the two astronomies had occurred. One can see how complete this fusion was by taking an example, such as the large 18th century Korean astronomical screen from the Yi dynasty's royal palace in Seoul, lately deposited in the Whittle Museum of the History of Science in Cambridge. Note: see Needham and Lu Guizheng, 1966b, Korean screen. To the right, it reproduces the classical planisphere of 1395, prepared for Yi Thai Zhou by Quan Kun and his colleagues, but though equatorial in projection, this bears the Chinese names of the Western zodiacal houses round its periphery. In the centre there are two Jesuit planispheres, ecliptically projected, and using the Western 360-degree graduation instead of the Chinese 365.25-degree one, yet conserving not only the entire pattern of Chinese constellations, quite different from the Western as we have noted, but even the age-old division of the stars into three colours, based on the ancient star lists drawn up by the 4th century BC astronomers Xi Shen, Kan Te, and Wu Shen. Note: Science and Civilization in China, Volume 3, page 263. End of note. To the left there are diagrams of the several planets, with text describing the new discovery of their moons and phases by Galileo and Cassini, and sunspots depicted on the Sun, as Chinese astronomers had noted them from the 1st century BC onwards. Further text described the resolution of nebulae, star clusters, and the Milky Way with the aid of the telescope. The Jesuit work preserved on the screen centers round one of the directors of the Chinese Bureau of Astronomy, Ignatius Kögler, and it must have been painted about 1757, not long after his death. Note: the circumstances of the matter have a special interest because in 1741 a Korean astronomical official on a mission to China, An Kuk Rin, had formed a friendship with one of Kögler's aides, André Pereira, whose real name was Andrew Jackson, the only Englishman who is numbered among the roll of the Jesuit mission in China. End of note. Another striking example can be seen in two Chinese optical virtuosi, Po Yu and Sun Yun Chiu, who lived and worked in Suzhou between 1620 and 1650, making apparatus such as telescopes, compound microscopes, magnifying glasses, magic lanterns, etc. Note: see Needham and Lu Guizheng, 1966b. Po Yu indeed may be numbered with Leonard Diggers and J.B. Della Porta, Lippershey, James Metius and Cornelius Dribble, and all those other figures involved in the invention of the telescope and the microscope in the West. It is quite astonishing to find that within a couple of decades seekers in China were hot on the same trail. We do not yet know, and perhaps we shall never find out, exactly how independent they were, possible Jesuit intermediation being in this case obscure, but one can certainly say that at a surprisingly early date, 1635, the telescope was being applied to artillery in battle in China, and there is a strong possibility that Po Yu himself independently invented the telescope by juggling about with combinations of biconvex lenses, just as a number of the inventors named above did in the West. Sun Yun Chu even wrote a treatise entitled History of Optic Glasses. Such was the extreme rapidity with which the mathematical and physical sciences of the Western and Chinese cultures fused after they first came in contact. When you consider an intermediate science like botany, you find a totally different picture. It has been most interesting to observe in work which my collaborators and I have been doing recently in the history of botany. Note: Science and Civilization in China, Volume 6, Part 1, end of note. That there was a long delay after the first contacts, and one might say that the fusion point in botany did not occur until about 1880. Down to that time, Chinese botany continued on its classical way. The naming, classifying, and describing of plants went on along traditional lines. Even as late as 1848, the indigenous style persisted in the important works of Wu Chi-chun, Illustrated Investigation of the Names and Natures of Plants. Though written at such a recent date, this splendid and well-illustrated treatise was entirely traditional in character, and did not take any account of the advances in botany which had been made by Camerarius and Linnaeus. It is important to notice here that the Jesuit mission of the 17th century did relatively little for botanical contacts. Indeed, what it transmitted was westwards rather than eastwards, as witness, for example, the Flora Sinensis of Michael Boehm, printed in 1656. Moreover, it could not have transmitted modern botany because its activity was both pre-Camerarian and pre-Linnaean in time. But when one comes to 1880, when Emil Bretschneider, the great medical officer of the Russian Ecclesiastical Exarchate in Peking, was doing his work on Chinese botany, then there began to be Chinese botanists who could speak the same language, could talk about Linnaean families and natural families, men who understood, like European naturalists, the function of the flower, and what the microscope could reveal of plant morphology. This was the time, too, at which centred the great effort of many investigators, indispensable for further development, to establish correlation as complete as possible between the Chinese traditional plant names and the Linnaean binomials. Note: compare the works of Bretschneider, which are still quite indispensable. End of note. Thus, one might say that it was not before 1880 that the fusion point took place in botany, and a decade or so later might be a better guess. Beyond this, when one passes on to medicine, one finds a situation in which the fusion of the sciences, pure and applied in East and West, has not taken place even yet. I dare say that this is the case because, although physicists don't quite like you to say so, and astronomers equally may demur, nevertheless the phenomena of these sciences are surely much simpler than those with which biologists have to deal, and a fortiori physiologists, pathologists, and medical men. Wherever the living cell is concerned, a fortiori the living cell in its metazoan forms of high organization, the puzzles are profounder, the tools both practical and conceptual more inadequate, the room for doubt greater. However optimistic one may feel as a young biologist or biochemist, the secret of life is still not yet just round the next bend. I speak from experience. Thus, the coming together of the two cultural traditions, the fusion of them into a unitary modern medical science, has not even now been effected. Many people, of course, when they think of Chinese medicine today, imagine it as some kind of folk medicine, something bizarre and quite outdated, some sort of meaningless curiosity. But in truth, these are all entirely wrong ways of reacting to it. It is, one must say, the product of a very great culture, a civilization equal in complexity and subtlety to that of Europe. Note: Palos, 1963, rightly emphasizes this. End of note. While conserving a medieval body of theory, it contains a wealth of empirical experience which has got to be taken account of. Just as in any other science, we can find many Chinese priorities. For example, the compilation of a great classificatory description of disease entities without therapeutic material, the systematic treatise on diseases and their etiology by Chao Yuan Fang in 610 AD. Note, there is no adequate translation as yet of any part of this remarkable work, but in the meantime a paper by Rowell 1962 may be referred to with due reserve. End of note. A whole millennium before Felix Platter and Thomas Sydenham. Or again, the first handbook of forensic medicine in any civilization, the Washing Away of Wrongs by Sung Chu, 1247. Note, partial translation by Giles, 1924. Appeared a considerable time before the European foundation stones of the subject, the books by Fortunato Fedele. Note, 1550 to 1630, Castiglione 1947, page 557, his De Relationes Medicorum 1602 defined the subject, and Paolo Zacchia, note, 1584 to 1659, Castiglione 1947, page 557, his Questiones Medico-Legales 1635 is the great landmark in the European history of forensic medicine. End of note. However, the rationale of some of the most important Chinese therapeutic practices, such as acupuncture, to which I will return in a moment, is not yet clearly understood. And obviously not all the drugs of the very rich traditional Chinese pharmacopoeia have yet been thoroughly examined from the biochemical and pharmacological point of views. Equally important, there has until now been little unification of concepts. The original stimulus for this study arose indeed from problems of translation and technical terminology. In all the inorganic sciences, Dr. Wang Ling and I found long ago that once you know exactly what the ancient or medieval Chinese writer is talking about, you can find the Occidental equivalent for his words without too much difficulty, and everything makes good sense. So, for example, one can converse with him across the centuries about solstices, qi, or equinoxes, feng, square roots, kai feng, or comets, hui xing, Lowitz arcs, Thi, rock salt and brachiopods, Shi Yun, written in two different ways, equally in the technological world about Norayas, Thong Chair, water-powered reciprocating engines, Shui Fai, or chain and link work, Thie Ho Shi. This is true only to a slightly lesser extent in fields such as botany and zoology, where Sui is a spike or raceme, and Thai a capitulum or flowerhead, while the corolla, Pa, is clearly distinguished from the calyx, O. Similarly, Wei cannot mean anything but the stomach of an animal, nor Fan Chu Wei anything but a rumen. Alchemy and early chemistry have their own special problems, exactly as they do in the West, and for the same reasons of purposive concealment and the like, but even amidst the spagirical flights of poetic fancy, there is far greater regularity than might be supposed, so that the river chariot, Ho Chair, always means metallic lead. Note, but caveat emptor of course, for in medico-physiological terminology the same words mean the placenta, and the food left behind by Yu the Great, Yu Liang, always means brown nodular masses of hematite, ferric oxide. China, moreover, had her Martin Ruland, but her lexicon Alchemia was nearly 1,000 years older than his. The synonymic dictionary of minerals and drugs by Mei Piao, circa 806 AD, and it is extremely useful still today. Similarly, on the technological side, Fan is always alum, Shichan always copper sulfate, and Huo Yao, the fire chemical, never means anything else than a gunpowder composition. On the whole, the terminology of medieval Chinese chemistry, though far from unravelled as yet, presents no fundamental difficulties. Dr. Ho Ping Yu and I have found that it is quite possible to make medieval Chinese alchemical writing intelligible, though many years must pass before all its secrets become known.